Hi everyone. This is the second video from a series of videos discussing why dawn in Indonesia is too early. Please follow the first video to understand this second video. We are from the Islamic Science Research Network, Hamka Muhammadiyah University in Jakarta. This series of videos is a summary of a book in Indonesian entitled The Evaluation of Dawn and Isha Times. Science, Technology and Sharia Perspectives, which was published on January 5, 2018. English and Arabic editions of the book are being prepared. To order the published book in Indonesian, please contact Hamka Press, phone or WhatsApp, +62 838 7266 8742. The conclusion of the first video. In the first video entitled, Why is Dawn in Indonesia Too Early? 1. We have delivered the average depression angle dip for the presence of dawn in Indonesia, which was estimated from 198 data. The average dip value is -13.29 degrees with a standard deviation of 1.85 degrees. The lowest dip value is -9.3 degrees, while the highest dip is -18.38 degrees. This result showed very reliably because none of the population members touched the threshold value, considered as the just non-detectable blunders. The upper threshold is the average value, plus 3 times the standard deviation, which is equal to -18.84 degrees. While the lower threshold is the average value minus 3 times the standard deviation, which is equal to -7.74 degrees. In other words, the determination of the beginning of the dawn time at the -20 degree dip as currently practiced by Muslims in Indonesia must indeed be corrected. As for the Isha time, we have 149 data with the average dip value -13.34 degrees with a standard deviation of 1.59 degrees. The highest dip in the population is -17.69 degrees. And the lowest dip is -9.35 degrees. These results are also highly reliable because none of the members of the population touched the threshold limit, the just non-detectable blunders. -18.11 degrees and -8.57 degrees. It can also be concluded that the dip of -18 degrees as the beginning of Isha time, which has been practiced by Indonesian Muslims so far, also seems to be way too late. Verification of the SQM results using the all-sky camera. In all human activities, there must always be a verification process. Some examples of the verification process in everyday life include: journalists practice the principle of covering both sides to maintain their independence. A bank teller always checks the amount of cash being deposited even though the customer is a highly respectable person. Reputable companies always use the services of independent auditors. Likewise, ISRN also applied several verification processes in its research by using several other sensors to detect the presence of dawn. Its main objective is to verify the results of the dip calculation from the SQM data. The first sensor we use for the verification is an all-sky camera, ASC, as shown below. All-sky camera image characteristics, ASC. An all-sky camera look like this. Basically, it is an ordinary DSLR camera equipped with a fisheye lens to capture the half hemisphere. Whilst the sample image is shown here, this is the half-hemisphere image by an ASC, whilst the image is dominated by black portion in its perimeter that is not really needed. We used an ASC Alpea 6 megawatts type having the following characteristics. It is a panoramic camera that capable of capturing half of the hemisphere within 360 degrees. It has a geometric resolution of 6,439,680 pixels consisting of 2,080 lines and 3,096 columns. It has an 8-bit radiometric resolution so that each frame needs about 6 megabytes of memory. On July 3, 2017, ISRN conducted the night sky photography from 5 hours 0 minutes and 4 seconds am to 5 hours 30 minutes and 51 seconds am with a temporal resolution of 7 seconds at our observation station in Depok in the outskirt of Jakarta. On the same night in the same place, we collected also the sky brightness data using an SQM. From the ASC data acquisition, we obtained 257 frames of images. For the efficiency and effectiveness of the image processing process, we applied a progressive sampling technique. The first level of progressive sampling is done as follows. Because the east is located here, and owing to the fact that the sun rises from the east, we then divide the image into 4 parts. Thus, we only have to process a quarter of the image with a smaller number of pixels. In addition, we also do not need to process all 257 imageries we have because we have the following data on July 3rd. 2017, in the Depok, West Java, the government's official dawn occurred at 4 hours 39 minutes and 34 seconds am. That is when the sun was at the dip minus 20 degrees. Meanwhile, from the SQM data we have, the real dawn actually occurred later at 5 hours 2 minutes and 51 seconds am or at the dip minus 14.7 degrees. Therefore, the next step in the progressive sampling is to compare the processed image at certain times required. The processed image we use in this case is the image's histogram and edge detection. To start with, we compare the histogram between the image taken at 5 hours 0 minutes and 4 seconds am and the image at 5 hours 2 minutes and 31 seconds am. Unfortunately, though, the first image used as a benchmark on the left was taken beyond the government version of the dawn that occurred at 4 hours 39 minutes and 34 seconds am. Meanwhile, the second image on the right was taken at 5 hours 2 minutes and 31 seconds am, or 20 seconds before the dawn appears according to the SQM data. We can see that there is no significant difference between these two histograms. Likewise, we can also do the image analysis by comparing the canny edge detection of the image taken at 5 hours 0 minutes and 4 seconds am on the left with the image taken at 5 hours 2 minutes and 31 seconds am on the right. The canny edge detection technique also failed in distinguishing changes between the two images. From these two image processing techniques, we can conclude that the dawn is not possible to appear between the images taken at 5 hours 0 minutes and 4 seconds am and at 5 hours 2 minutes and 31 seconds am. In other words, it was impossible that the dawn had occurred at 4 hours 39 minutes and 34 seconds am as suggested by the Indonesian government. The second stage of the progressive sampling. The next step in progressive sampling is by comparing a histogram of the image at 5 hours 0 minutes and 4 seconds on the left, with the image at 5 hours 5 minutes and 6 seconds on the right, which is taken about 2 minutes after dawn as estimated results of the SQM data. There are no differences between these two histograms. In the left histogram, the number of black pixels is around 130,000, as well as on the right. From the edge detection image comparison at 5 hours 0 minutes and 4 seconds on the left, with the image at 5 hours 5 minutes and 6 seconds on the right too. It doesn't show a difference. Not yet seen the appearance of different spots between the left and right images. It can be concluded, the all-sky camera is apparently unable to record the appearance of dawn detected by the SQM at 5 hours 2 minutes and 51 seconds am. The reasonable reason is that the ASC image is too dominated by the black part in its perimeter of the image that is not needed. This is the biggest weakness of ASC's image. This black section has become a serious disruption in the image processing process both in the histogram and the edge detection techniques. A histogram difference can only be detected when we compare images at 5 hours 0 minutes and 4 seconds am on the left with the image at 5 hours 15 minutes and 1 second am on the right. The spread of the histogram in the picture on the right has begun to change. Likewise, if we compare the spots on the results of edge detection of these two images, these differences are increasingly clear if we compare imagery at 5 hours 0 minutes and 4 seconds AM on the left with the image at 5 hours 20 minutes and 2 seconds AM on the right. The presence of dawn on the right image can be seen clearly through histograms and edge detection results. The spots on the right picture appear more distinguishable. We, therefore, can conclude that at 5 hours 15 minutes and 1 second AM, the all-sky camera was able to detect the presence of dawn. However, it must be remembered that the SQM has been able to detect the presence of dawn at 5 hours 2 minutes and 51 seconds AM. This means the ability of the all-sky camera to detect dawn is around 12 minutes late when compared to the SQM. Conclusion: the all-sky camera is not suitable to verify the presence of SQM's dawn. This is due to the fact that the all-sky camera images are the predominantly black section on the image perimeter that we do not really need. However, this black part has become the serious disturbances in the process of the image processing. As a result, rather than proving that dawn should have appeared at 4 hours 39 minutes and 34 seconds AM like the Indonesian government suggests, the dawn of the ASC verification results was even behind about 12 minutes compared to the dawn of the SQM. In the next video, we will discuss the use of other types of sensors to detect the presence of dawn. Thanks for watching.